All right. Hey, what's going on, guys? It is Ryan at Exoderma again, an exponential world. Today, for our first episode, what we wanted to cover, Lou and I, by the way, say hello, Lou.
Hey, how's it going, guys? Just Lou over here, just the CTO, just sitting over here. It's all good.
He really is, though. All right, okay. Tech brain. Okay. We wanted to cover a specific topic today, and the specific topic is sort of an intersection with what we are working on together, as well as the current societal epidemic. And that epidemic is specifically a pandemic. And so what we're going to cover today is machine learning and COVID. So just to, before we go too deep into what I wanted to bring news of between machine learning and COVID, I really want Lou to go over really quick sort of what machine learning is and how it relates to artificial intelligence, just sort of like a broad overcast so people get it, or at least get a part of it.
Sure. So machine learning is a subset of artificial intelligence, and machine learning deals with the process of giving data information to a computer and designing a carefully thought out model that takes that information and is able to produce an output or a prediction that very closely relates to the original data's outputs or true values, right? So it's that way, and it could be any type of data. You can get numerical data, you can get audio data, you can get categorical data. It's really a matter of figuring out what kind of information you need to be able to relate, what you're studying, what type of thing you are looking or interested in. And in this case, if you're interested in COVID stuff, you could get information in the form of images of people's lungs. And the truth that you'd be feeding the computer would be if that image is of a person that had COVID or not. So by feeding those images to the computer, you can get the computer to predict if another given image that you don't know yet is related to a person with COVID or not. So it's a pretty interesting way to teach, quote unquote, computers how to make inferences and predictions.
Would an analogy be like if you were walking and there's a wall to your left, or you're walking in a maze and you take a left and there's a left and a right turn and you don't really know which one leads to which, but you give it enough times of doing it, you can make a probability estimation of which one led to not the dead end.
Yeah, if you were given enough examples and you did it enough times, you start getting a pattern or an idea of what the pattern would be.
Okay.
And you're always going to have some error, never going to be 100%, but you're at least getting closer to that 100%, which is good.
So the machine learning, the agents or whatever they're referenced, that their job is to literally discover some mathematical pattern in the data.
It depends, actually. Sometimes it's simpler than that. Like you can have a model that's already like a linear model, right? Like you're saying that as you vary one variable, the other variable also varies in some linear fashion. So that right there is you imposing the model and trying to see if it fits. But there are certain models like neural networks that they do what you're actually telling us, that they figure out the pattern themselves. We don't give it any pattern to initialize it with. It just figures it out. And it's actually a black box to some people. They don't really understand what's going on in the modeling. They just see that it works.
Wow. So that's what you mean. So these things don't need any pre-trained. They don't need any data to be trained. They just need the problem to be done over and over and over again.
Right, with the correct answers at the end. Well, that's in the supervised case. There's an unsupervised machine learning, let's say, way of doing things. And that is a little more complicated to get into, but it's also out there. Like there's ways of not knowing the answer right ahead of time and somehow getting the computer to predict the correct answer just based on the data that it was given. It's based on clustering and analyzing high dimensional spaces and getting things that are closer to each other to be, the next time that you get a data point, you see what that data point is close to in that space, and you can predict that as your answer.
Interesting. So it's like updating itself as far as the predictions go based on every new input of data.
Exactly. Yeah.
Okay. So to get into our specific use case, Lou did mention it a little bit. So specifically, UC San Diego teamed up with Amazon Web Services recently to increase the accuracy of identification of pneumonia. The reason they chose pneumonia as identification, or at least a metric to identify things, is because it's closely linked with COVID-19. And so the way they've done this is actually, he mentioned it, is to take these x-rays of lungs and pass them through a machine learning, a neural network that's able to essentially increase the probability of predicting whether or not someone has pneumonia. Now, to me, this is super important because it's a step above the human eye. So it's, I'm not necessarily a step above the human eye. There's actually a couple ways this article presented it. Our article presented it not necessarily as something better than spotting pneumonia with the human eye, but more as a way to automate the task of potentially identifying some sort of respiratory issue. In your mind, like, how do you see going about plugging lung x-rays, and like, what, is there a specific tool set you would use? I mean, it's computer vision, so this is your area. What's your reality on this?
So from what I've been implementing in the past, I think the way that I would go about it would be through transfer learning. And that has to deal with, like, there's these models that people have been training already, right? These people at Google, Facebook, they've all been feeding them tons and tons and tons of images. And that trains them and gives them weights, certain weights, right? So you take these models that have been trained for some other task, or whatever it is, either classifying 1,000 different objects, right? And you take the last layer or the last 2 layers of that neural network, you chop it off, and you now retrain that model on your data set, which would be the COVID lung images or pneumonia images or whatever it is you're interested in. And so that model has mostly all of the old weights from Google and Facebook's training and all their training has those weights, but it's also updating its last few layers with the new problem that you're throwing at it. So that's why it's called transfer learning, excuse me. And so what it can do then is just train those last 2 layers, which would be super quick. You know, it's not that many weights to update. Whereas it already has those other 1,000, maybe 1,000 layers that have already been trained. So those are going to act the same because it's object recognition, it's image analysis. So those fundamental layers will probably be the same no matter what problem it is. It's only the last couple of layers that need to get updated because it's a different problem. So yeah, I would probably do some transfer learning on some model that's already been created by Google or somebody and just feed it in the images and update the last layers of weights. And that would probably give you a really, really super accurate model.
So you're saying that okay, so in this model that these people have spent hundreds of hours and putting the data in to train these models, these machine learning models, that they establish parameters and weights in the first couple hundred layers or however many layers it happens to be. And these layers are, in my mind, these are sort of like features. These are features. Like, these have features.
Exactly.
Or they are features.
They are exactly
features.
That.
Okay, and so these features are essentially being the ones that are successful for the, okay, so
the features that they pick out are based on, like, how would we put it, like lines, you know, like they can see like what's like a line or something or some type of pattern that's recognizable on a low level.
Interesting. So it wouldn't even necessarily it wouldn't matter what the image is because it's not seeing it's not seeing it. It goes back to my mind and how this is processed. It's not seeing what we're seeing. It's seeing zeros and ones. And so it's specifically looking for those things that we see or don't see, and is able to actually take so much data. So it's like a savant. It's like a savant. You're talking about a savant genius computer that's able to memorize one specific thing, and then, like, rather than giving it the same kind of problem it's been solving, you give it a slightly different problem. Because the problems are all related, the savant has no problem at all finding something that's relatively accurate compared to other standards, just because it's the same tactic. It may not be identifying lung issues specifically, but it is an image issue nonetheless.
Yes, exactly. So there's always going to be like edges. There's always going to be, you know, contrast and colors in an image. And so those types of features get picked up somehow by the machine learning model mathematically.
Yeah.
And that's how it's done pretty much.
Wow. So in this particular thing, like, we're talking about pneumonia and lungs, but this could be applied to a range. Like, so we're talking about computer vision as far as looking at X-rays. Um, brain scans, MRIs, you know, are what else can this be applied to identify? Like anything?
It goes really far because I've read about cases where they use it for forest fire detection and predicting where the next forest fire will occur, so they have a better opportunity. You know, and it also goes into how much data can you get. So they don't only use images for that forest fire problem. They also use temperatures and wind pressures, and there's so much data that they give the machine learning model that it's able to get to those ridiculous levels of predictions.
Dang. So it's and this is the whole case. So in my mind, like a successful model will be a model that has features that are more impactful on the result. So like a really
Yeah,
accurate
feature
model is a.
importance.
I'm sorry.
They're called feature importances.
Okay. Okay. So yeah. So like a really accurate model would be a model that has a specific set, like limited amount of features, but has really high accuracy. My question is, it sounds like in a lot of these models, there is no preset parameters per se. It's just the collection of weights that may or may not affect the outcome. Is that sort of like what we're looking at? Like as far as taking in data, air pressure, wind pressure, we're getting a lot of all this other data, but is there a point where
Yeah.
data
So
becomes,
So the way that part of it works is you initialize the weights randomly. They're initialized randomly. There's no like you say structure or anything to them.
yeah,
And so your initial guesses for the predictions will be all over the place, right?
yeah.
But you have the ground truth values to compare your predictions to. And so that difference in the ground truth and your prediction gets it's called back propagation. It gets back propagated through the network to update the weight so that it gets closer to the actual value that it's supposed to predict. And it just goes back and forth predicting and back propagating the errors so that it keeps updating the weight that you initially chose as random, but then later becomes not random and later becomes an actual predictive predictive capacity.
Wow. Okay. So then my next question would be that hypothetically, could you create a machine learning model off of variables that were high weight variables? Like let's say you just wanted a machine learning model that had 4 layers, so there are 4 different features. Hypothetically, could a model? So if I wanted to model this potential for fire, could I model the season of the Earth, the side that's facing the sun, you know, and specific variables, very few variables that are pretty large, or I'm sorry, features that are pretty large. Could you do that too? Or is it just, does it have to start from like a random space?
I couldn't hear that last part. I'm sorry, my internet was a little off.
Oh, you're good.
Can you say
Okay.
that again?
Yeah. So, could you have a machine learning model that starts with few like features that have big results on the impact that you could like, is that possible? Or do all machine learning models literally just like start off from ground zero truth and then building out from there?
Yeah, so I guess it depends on the whole supervised versus unsupervised machine learning. So the supervised, you definitely have to have the ground truth answers given to the model. For unsupervised, it's not the
Oh.
case.
So we're getting into the differences of artificial intelligence application, like the different tools that you can use within machine learning to actually solve something.
Yes, exactly.
Okay, all right, that makes sense to me now. All right, well, that answers pretty much, I mean, it answers all my questions technically as far as using this to solve things. My next question though would be, in this article, they specifically talk about machine learning being used to automate the identification of pneumonia in the lungs and therefore potential of someone having COVID. Do you see machine learning as something, at least at this point, as something that could be used? Is it more of an automation tool or is it a solution? Like, do you know what I'm asking? Do you see what I'm going towards with this one or no?
Are you kind of trying to relate it to like what an AGI would be capable of doing?
I guess so. I mean, more so, I guess, I mean, yes and no. Like, for instance, these machine learning models are specific, right? So the job they do is very specific. My question is like, okay, so in order to identify COVID identify pneumonia is one thing, and then you have to identify something else, and then you have to take another step to do this and this step to do this. So obviously machine learning is one small chain of that. But in that particular context, it's just a solution. But can they be stacked together as I guess to automate a job, a full-on job, or?
Yeah, so that would definitely already be what is considered as artificial general intelligence, right? Where the whatever it is, that program can decide what model to use based on its analysis of what it's dealing with. So we don't have any way right now of a computer deciding what model it should use. You know, the engineer or the data scientist at the end of the day has to decide what model they're going to try out, see if it works. And there's no actual way of saying, oh, I know what machine learning model to use for this specific problem. It's sometimes really a game of guessing and trying to, like, intuitive guesses, you know, and like educated guesses, but guesses nonetheless. Sometimes you'll try a random forest model and it'll perform great, but you won't know why. Or sometimes you'll try a convolutional neural network and that will work great. And that's usually used for like images and audio data. But as far as like having a machine itself decide what model to do and like train itself and do those things, I think we're not there yet.
Okay. So would you say a machine learning model, like I guess sort of like the objective of machine learning is to get down to first principles, essentially?
It might not. Sometimes the researchers are sometimes not sure what the machine learning model is, how it's modeling it. So whatever it's doing, sometimes it's a black box. So there's still, like, sometimes you throw a random forest at a problem, right, which is a type of machine learning model, and it'll get the answers correctly, like 97%, 98% of the time. But if you ask the researchers, like, how's it doing and what model is, how's it actually, you know, working, they have no idea. There's no real way to actually even look into the model. It's so complex. But yeah, that's how it sometimes works.
So sort of so machine learning at this particular point in time is literally just trying to apply it to as many things with as many data sets as you can to figure out if there's any correlation to some upside, whatever the upside may be. And
Yes.
the real constraint is not the models themselves, because we have the models. The constraint is literally data.
Yeah, definitely data and having the people necessary to smart enough to figure it out. So it's still the humans that are
Yeah.
trying to figure it out.
Okay.
Machines are still our slaves, I would say. We aren't the slaves of the machines yet.
But like, so if we were to scale, like, hypothetically, if you were to like, okay, so I'm just thinking, like, if you could hypothetically collect the what would be a good random variable? Hair length of every single human on Earth, you could probably, no, that wouldn't make any sense. There's no end result there. I'm looking for something with an end result that you could collect all the data possible.
The stock market data from the last 50 years.
Okay, but the problem with stock market data is that it doesn't actually regress to the mean. It's like this, I mean, it does and it doesn't. Like, I don't know, I've been reading this book on, like, okay, so we have access to all this data, but we can't predict it. So then therefore, I don't know, the data will be bad then, or what?
Sometimes it also depends on like, sometimes you can have a lot of data and it wouldn't actually help you out because you would start maybe trying to fit your machine learning model to the noise that it's coming out with, right? So it becomes actually a trade-off between bias and variance, which are some concepts that we should probably talk about either now or in the near future because they're important. But yeah, it's a problem of, if you give it too much data, it might be overfitting to that data, right?
Mm-hmm.
But then some new data point comes along that is not necessarily too related to that data set, but still part of the problem. And it will be too in love with the data that it's been studying that it'll predict in that, you know,
Wow,
that's called
yeah.
variance. So yeah.
Biasing the machine learning model, or biasing the model, I guess. Okay, so it's sort of like Facebook's whole thing with, so like, as a marketer running Facebook ads, the beauty of Facebook is that you can hyper target just about anyone you can think of, their personality and what interests they may have. The downside is that this can be politically used, right? And so, like, what's happened as a result, a natural side effect, is that their algorithm has been biased towards politicizing things, and they're aware of that, and they're I guess trying to curb it maybe at this point. But what you're saying essentially is that the model itself has sort of fallen in love with a particular type of targeting data, or to target people off of, and as a result reflects it, like,
Yeah,
like humans, like what, like we do as people.
exactly.
Wow.
So not only depends on the amount of data you have, but you also want to have data that's distributed, I guess, evenly in a sense, so that your machine learning model doesn't bias or isn't biased, or doesn't have, you know, that just wanting to go to that one area that it's been studying.
So, for instance, if we were going to try to identify COVID or identify pneumonia, we would probably be better off feeding it, let's say hypothetically, feeding it 10,000 lung x-rays of people who do not have pneumonia, and then feeding it some ratio of people who do have it and being able to identify between the two, rather than identifying just x-rays potentially having COVID and potentially having pneumonia. But that's where the supervised learning comes in, where we could actually target it with, this is the solution, this is what we want to find. Anyone who doesn't match this, or anyone who does match this, interesting. So you can, wow.
A lot of machine learning problems rely on the fact that you know the answer from some data set, right? You have some history of data that has the answers along with it. And then the machine learning model picks up on the patterns necessary to you know, relate the features to the answers. So it's sometimes difficult when you don't have the answers to the problem you're looking for. That's when you really have to be clever and do other things outside of the regular toolbox that's available to machine learning engineers and stuff like that.
So sort of what we're kind of what we're doing right now in a way, or mostly you're doing in a way with the posture and everything. Mm-hmm. Like you're kind of going outside of the box to handle this problem.
Yeah, and actually I was looking at some examples of how they do it, and it's actually painstakingly crazy, like how they have to hand annotate each image that they have in the data set before feeding it into the model, so that you have the ground truth of where the joints are.
Yeah.
Yeah.
So my question would be so then that's where we talked earlier about, like, where we would use, you know, you could use accelerometer kits or the 3D Vicon, and you could actually train the model in a different way without having to annotate anything.
Yeah, that'd be one way. But it actually also, it depends if you have the position available information too.
What do you mean position?
Like
in 3D space?
Well, it depends on the problem we were doing. So if we were doing pose estimation, you would need some form of position data. But if we're doing acceleration analysis, then I guess the position is irrelevant if you already have the acceleration data from the accelerometers.
So that was my question, right? So like hypothetically, I mean, no, because you still need pose estimate. You still, I was just trying to think of their different, like, never mind. That's a dead conversation I do not want to have on the podcast. We will save it for 3 years from now or 18 months from now when it's safe to share. Nonetheless, we've sort of dug deep into machine learning, relatively speaking, and sort of identifying, I guess, similarities between different types of data would be what it would be a way to simplify it, right? So yeah, whether it's an image and different layers of that image, contrast, brightness, whatever it may be. And then on top of that, sort of into what potential so is there a limit to the applications this can be applied to? Would be my last question. What can't you apply machine learning to?
I think if you don't have the answers already, that's a possible limitation. Like you have to have some form of already historical, modeling of your problem. Like there has to be a lot of data that has already been picked up, and a lot of answers that have already been included with that data. And that's when machine learning really shines. That's when it becomes like ridiculously good, and you see like all these crazy applications like we've been talking about. But when you don't have it, that's right now the issue. That's up in the air. That's really up in the air.
So integrating this technology, as I mentioned in the previous podcast, like our previous intro podcast, or maybe in the beginning of this one as well, literally integrating machine learning is completely based upon how efficient someone is at collecting data and applying the answers they found. And that's essentially like that's like the integration issue with machine learning. It could be amazing if we had a whole bunch of people who were decided to collect data about just about everything that we had modeled already. Then we could apply it to machine learning, but I would say that's not happening at scale right now. Most people are sort of not really looking at machine learning in that sense, or are they? I don't know.
Right. So I don't think they necessarily are, and that's where the focus should, I guess, go to picking up good data that has, you know, the relevant answers to them, so that you can get a machine learning model to model that and be able to predict it without you having to get into the theory or into the like crazy mathematics of what's going on in that system, which could still be, useful in some cases. But I think that more and more people are just going through the whole throwing a lot of data and just trying to get the computer to figure it out for them.
And probably giving up whenever it doesn't figure it out for them, or moving on to some other model and then going through that same process.
Yeah, that's when they try to go into the unsupervised type of learning. But that also is difficult to figure out, like what's going on, like what sometimes the problem statement should be, or how to go about figuring out the right answer, or sometimes even checking if the right answer is the one that is being output.
Interesting, because you could hypothetically be feeding the wrong answer to something, and it wouldn't know it. It would just be trying to output an answer, because there's not a wrong answer to it. It's just an answer. It's just like if you give it a result, it's just a result. It's not good. It's not wrong or right. It's just a result. So it's trying to match that result.
Yeah. So usually they have what's called testing, validating. Sorry, let me start that over again. Training, validating, and testing sets. Right. You have your data, and you have to split it up in those groups.
Yeah.
So you feed your machine learning model the training data, right? And you compare it to the validating data that you split out, right? So those two things right there are what trains your machine learning model, and you try to get the best accuracy or whatever score you're trying to measure with that model. And then once you're done training it, you go to your testing set, right? The third option that you have, and that's actual like real world data. That's like data that your machine learning model has never seen before, and you actually base your performance of your model on the testing data. So you need training and validating to train, and then you need the testing to actually test and see how your machine learning model is performing. So sometimes it also requires you to have a large data set so that it can actually be split up into those three categories.
Yeah, so it literally is like, yes, I think yesterday or the day before yesterday we spoke, and I was talking about how I guess an issue would be that a lot of the people who are using machine learning as a tool to solve problems don't necessarily, I mean, they have access to data, but they're not thinking about acquiring data in the same way a corporation would acquire data. You know what I mean? So in order for them to they'll have a certain limitation on the accuracy of the models they could even obtain just because of that one factor alone. So I guess they're really like, where does someone start? Do they start with data first or a model first, or a problem first? I mean. Some data or a problem?
I'm pretty sure it usually depends on what area they're doing. But the way that I do it is I have a problem right in front of me, and I got to figure out what's the relevant data that I need that would give me some form of, predictive power in that case. So in, like, let's say the computer vision model that we're working on, right? I wouldn't need other information besides the images that we need from the camera, right? That would be my primary source of data that I would be asking for. That's why I always ask you for, punches of people, performing the punches in front of a camera. And I don't think I've asked for anything else because there is no other type of information that I could use for this specific problem.
That's sure. I mean, you could hypothetically tie in other data sources to just clean up the data, make it more accurate, the result more accurate. But realistically, you really only need one source of data using computer vision, which is vision.
Images, yeah.
Images, yeah. I was thinking about it in the context of, like, biologically speaking, some of the most successful species happen to have eyes. In fact, I'm pretty sure the majority of them have eyes. And they were all developed in different ways under different contexts and different environmental stimuli. So it's like, it would make sense that that the computer vision is something that's so applicable, like not just to COVID, not just to posture recognition, and not just to there's so many things I can't even think of any other things. Like you mentioned something global, like potential fire. Like that's an incredible. To have any level of predictability there is pretty interesting, even if the accuracy isn't like 100% or 60%.
Yeah, I'll share another application with you that I heard about, which is security camera footage. So there's security cameras, right, outside of businesses or whatever, and they usually capture like a person that's up to no good, right, walking around trying to see like what's scouting the place out and stuff like that. And they use computer vision to analyze a person's motion and see if they're sketchy, right? And then like, what's the probability that this person will commit some type of crime based on the way that they're moving? Because there's a certain movement pattern that goes on in humans when they're under stress and, you know, planning something, and, you know, those things are there's data, information is there. So yeah, that's another application that maybe, you know, is not so commonly talked about.
Well, it reminds me, so another uncommon one, which maybe many people will be fearful of, is China. And they use actual posture recognition as a secondary format of identifying you as a person, right? If you would assume that everybody has some kind of kinematic difference in the way they move, especially in like how long their humerus might be versus some other human, you really get to this point where if you can measure accurately enough with a computer camera or the camera, then you could identify someone just off of the way they're moving without even seeing their face. Unless they went through some drastic change.
Right. Their movement patterns are difficult to change. You know, the way they walk, their gait, the way they swing their arms, all the angles that are essentially, you know, part of their movement process would you just feed that into a computer and it'll be able to predict who that is.
Yeah, that's a scary, interesting. I mean, scary, but also interesting, like application of it, because you really think like,
if you think about it though, we do something similar, right? Like you could see like a silhouette of a person, and just based on the way that they're moving or walking, you could be like, oh, that's my brother, or oh, that's my cousin, or something like that. Something, you know, like,
we just don't have that kind of data retaining capacity.
Yeah. We only could do it for a few people. We won't be able to do it for like 1,000 people in a stadium, but the computer could, because it doesn't have, it's only limited by the memory capacity.
No, that's so true. Like, it really makes me think, it really brings into context what a census will look like in a few decades, maybe a decade, 2 decades, 3 decades, but what census will actually occur. Like, will you have to even fill out a form anymore? You know, would it be enough for you just to have walk by Food Line or whatever grocery store you're in for it to be able to identify that you were there, you know, and maybe tie, like, I guess it gets into this real level question of like how many services can be integrated, you know, would eventually Food Line or Amazon Organic Whole Foods would eventually identify you without using your Amazon account or your phone. You just walk in and walk out. That's simple.
Yeah, that's gonna be a thing. That should be like possible. It's gonna happen.
All right. Well, we've had a great podcast with this first episode, guys. We're gonna continue this conversation off podcast, but it was awesome to share this with you guys. We're gonna do our second podcast here shortly on another topic to do with technology and human society and solving our problems. I don't have any departing words. Do you have anything to say?
Yeah, I mean, I just have a question for you real quick before I say my last words. This is going to be posted on a few outlets, right?
Yes.
Okay, so if it's going to be on YouTube, something like that?
Mm-hmm.
Okay, so I would tell the viewers, whoever is viewing this, if they have any questions or comments or concerns, whatever it may be, to, you know, post it down below, and we'll pick that up as part of our next podcast. You know, if there's any questions that we see that are interesting and related to what we're talking about, we'll definitely include them in our conversation.
That's a really good point. Yeah, thank you for saying that. I completely skipped my head. Yes, please do that, because Lewis is really smart. Lewis is really smart, and Lewis can explain a lot of things to people who don't understand them, and so he's a good teacher. So yeah, ask your questions. We'll love to answer them. Yeah, take care, guys. Thank you so much.
All right, man. See you guys.